certain factors in my own brain.
Okay, let's let Don respond.
Right. Yeah, there's quite a bit there. So on the nature of the physical world and computation, um, and the finiteness versus continuity of space-time and so forth. I think that the work, Gödel's incompleteness theorem is very relevant here. That the notion of truth is far deeper than the notion of proof. There are any system, any computational system will have things that it can prove, but there will be truths that computational system cannot access. And if you add a new truth of a Gödel statement to your set of axioms, then there will be yet more truths that cannot be accessed from that. And so what you can compute is always going to be trivial to what is true. There will always be, as far as I can tell, again, it's sort of like Newton's notion of we're at the seashore and the vast ocean of reality, of the truths. He actually used the word truth. The vast ocean of truths is out there beyond what we can compute. And every truth that you add to your base for computation doesn't solve the problem. And you might say, well, that's true, of abstract mathematics, but that's not true of physics. I mean, the physics itself is computable, but there's some recent work suggesting that that's not the case. So Tony Kubit, a physicist, and his colleagues have recently proved that a very important problem to condensed matter physicists, called the spectral gap problem, is not computable. And that's a stunning result. And they also suspect, and they're working on this, they haven't proven this yet, but that something that's a big open problem, I think the Millennium Prize Committee this is one of their problems, is to understand the Yang-Mills gas gap problem, which is, why do photons and gravitons have no mass, but the carriers of the strong and weak force do have mass. And Kubit and his collaborators think, again, that we're going to find that something non-computational is going on here. It's not decidable. And my guess is that this is just the beginning, that we're going to find that as powerful as computation is, and, I was in the artificial intelligence lab at MIT for my PhD, and I'm all for AI and for computation, and I think it's fabulous what computation can do, and the naysayers who think that the computation can't do amazing things and artificial intelligence can have important limits that I think that I disagree with the naysayers. On the other hand, I do believe Gödel's incompleteness theorem is correct, and I do think that the notion of truth is just vastly the set of truths. I'll put it this way: the set of things that we can prove from any system is essentially probability zero in the set of all truths. In other words, we're always going to be, as Newton said, on the seashore with computation, and it's for principled reasons. So it's not a Mysterianism that's not founded. It's saying our best theories tell us that truth and proof are not the same thing, and that proofs will always only leave you on the seashore. And so that's why, I didn't like that conclusion, but, Gödel proved it, and now physicists are finding it in the spectral gap. And so as much as I like computation, I'm a computer scientist myself, as much as I like computation, I have to defer to the mathematical proofs that say computation goes thus far and no further. And then ask myself, okay, so my conceptual system then is itself just a symbolic system with derivation rules. So what I can compute by my thought is also going to be limited, which is why I was saying up front what I think about scientific theories, right? Scientific theories are going to have these limitations. We will put down a set of axioms. each theory, a good scientific theory, will tell you exactly what it assumes. And it will also give you a hint about the kind of derivations that you can give from those assumptions. And then you find what that theory will entail. But our best theories, like quantum theory and relativity and evolution by natural selection, the best theories will also tell you where they stop. They will say we go this far and no further. And for example, physics tells us that space-time itself cannot be fundamental, that the very notion of space-time cannot be fundamental, which is stunning because physics for several centuries has essentially been the study of what happens in space and time. And so to say that space-time is not fundamental means that the physicists have to redefine what physics is about. And that's what, for example, Juan Maldacena and Nima Arkani Hamed are trying to do with things like the cosmological polytope and amplituhedron and so forth. They're finding structures where there are no Hilbert spaces, so there's no quantum theory, there is no time, there is no space, there are these positive geometries. And what you find is you can predict events in space-time, like scattering processes that you see at the Large Hadron Collider. You can predict them, and in fact, you can actually compute them in some sense better than if you assume space-time. So they're finding that if you use Feynman diagrams and try to compute scattering amplitudes for 2 gluons coming in and 4 gluons scattering out, using the standard quantum field theoretic approaches where space and time is assumed, you get hundreds of pages of algebra, and it's a mess. Whereas if you let go of space-time and look at these structures with symmetries that cannot be expressed in space-time, like dual conformal symmetry, then you find that the same scattering amplitudes can be processed in just 2 or 3 terms that you can write down pen and paper on a sheet of paper. So all of a sudden, so what they're seeing is space-time has had a good run, but if you force yourself to stick with space-time, then the math is ugly. You get hundreds of pages of algebra to compute scattering amplitudes. You can't see the symmetries that are there, like dual conformal symmetry. If you let go of space-time, you're finding these amazing structures that they don't know what they're about, but all of a sudden you see the right symmetries and the computations become trivial. So there's some big hint that I think on a couple fronts, from Gödel and from the work by Tony Kubit and his team, that the computation is as powerful as it is, and as much as I love it as a AI person and a cognitive scientist, it's always going to be on the seashore with Newton. And when we let go of space-time, we're still, of course, as theorists, always going to have a finite set of axioms and derivations about, like the cosmological polytope and so forth that Nima and Juan are finding. We're still going to have a finite set of concepts and derivations. So we're not going to get around Gödel's incompleteness theorem, but at least we're going beyond the notion of time, which is really critical. And that also cuts at the computational issues pretty interesting. Computational complexity is about, a lot of it is about time complexity. And what physicists are telling us is that ultimately we're going to have to let go of the notion of time. And so as computer scientists, we're going to have to rethink complexity issues when the very notion of time itself isn't fundamental. So that's going to be a real kicker for us in computer science. How do we think about complexity issues when time itself is not the right way to think about things? And therefore the sequence of computations in time is not the right way to think about things. We have some really deep thinking to do ahead. But where I think we share some common ground, Yosha, is I think that a lot of our experiences and so forth are models that we build. I think that we are building internal models. But the question is, what is the apparatus that's building those models? And I'm saying it's nothing inside space and time. So in particular, I'll be very, very explicit. I don't think that neurons exist when they're not perceived. I don't think space-time exists when it's not perceived. I think neurons and space-time and even particles are simply data structures that we use. And there's a formulation of quantum theory that's very similar to this. It's called cubism, quantum Bayesianism, Chris Fuchs and David Mermin, where they take this point of view that it's every act of observation in physics, every experiment that you do is an act of fact creation, right? That it's not that there are pre-existing particles with pre-existing states and you're measuring those states. Rather, they're subjective Bayesians. So all the probabilities in quantum theory are subjective probabilities. They're not objective probabilities. And every outcome is a fact creation. And they do have, I mean, Chris Fuchs has a very interesting 2010 paper called Cubism that I highly recommend. And in that paper, he actually points to a very interesting quantum discovery, that there's a sequence of what's proven is that even if you know what the outcome of your experiment is going to be with probability 1, that does not entail that the outcome is there and exists independent of your observation. That's a stunning thing to say. It's a probability 1, you know with probability 1 what you're going to measure, and yet you can prove with quantum mechanics that it's impossible that the outcome was there, the value existed before you made the measurement. So that it's really the case that the acts of observation are fact creations, not fact discoveries. So most of the work that's done in consciousness assumes, and I would say this is 99% of the theories that I've seen in consciousness, assume that space-time is fundamental, assume that physical particles are fundamental, and that somehow neural activity in humans, and perhaps other kinds of more complex activity in AIs, creates consciousness. But the very founding assumptions that space-time is fundamental, that neurons exist when they're not perceived, contradicts our best physics. And it also contradicts evolution by natural selection, which is very, very clear. Natural selection makes it very clear that the probability is 0 that the sensory systems of any organism tell them any truths about objective reality. They tell what they tell organisms. Sensory systems evolved to tell organisms how to behave in order to stay alive. Period. That's it. And so that gives you a user interface for staying alive, but gives you no access to the truth. And that fits with what physics is telling us, that space-time is a user interface, but it's not the final truth. And so what I want from a theory of consciousness as a scientist is I want a clear statement of what am I assuming? What are the exact things that my theory takes as primitive? What are the exact rules that allow me to derive things from those primitives? And how exactly do I get the taste of chocolate from that? That's what I'm looking for from a theory of consciousness. Precise statement of exactly what I'm assuming up front with mathematical precision, and then precise derivation. If I'm not taking the taste of chocolate as fundamental, if I'm saying that somehow some dynamical system is going to give it to me, then I want to know exactly which dynamical system is giving me the taste of chocolate and why that dynamical system could not be the smell of garlic. I want to know exactly. Otherwise, there's no real science on the table at all. So that's what I'm looking for, is theories that say exactly what the assumptions are and tell me exactly, for at least one specific conscious experience, how that conscious experience must be derived in that way. And so that's where I'm coming from on those. Now, in the case of cells and the brain, I would just mention something that's very interesting. That's, you probably know about Mike Levin's work, right? And so he's finding that cells, not just neurons, but any cell in animals that, in fact, outside of the brain, they can learn, and they can compute, and they can do morphogenesis of the cell's body. They use gap junction communication, so they're effectively doing what neurons do, but in a very, very different way. And this is all cells can communicate in this way with gap junctions and so forth. So I suspect that we're going to find that neurons aren't special in the sense of being information processors. That information processing, and this seems to be where Mike is heading, is that information processing is happening in what he calls these bioelectric fields, even if there are no neurons. And they can learn, they can retain memories, and they can be very intelligent. And so even as neuroscientists, we may find that we'll have to expand our horizons beyond neuroscience in understanding. If I were a reductionist and trying to do biological reduction, I would, at this point with Mike Levin's stuff, be interested to say, well, maybe I wouldn't necessarily reduce consciousness to neural activity. Maybe these gap junctions and the computations that cells can do would also be a suitable format. But again, I'm not a reductionist in that sense. But I'll stop and let you respond, Yesha.
Thank you. You went very far and wide and try to be a little bit more concise. Let's start out with Gödel. Gödel's proof had a very profound and not necessarily very positive influence on philosophy. And basically, Lukács and others in philosophy opened up a tradition that where the underlying current is that what Gödel has shown is that mathematics is impotent to describe reality. And therefore, reality can only be described by people who don't really know mathematics, that is, philosophers. So philosophers like that intuition.
Right.
But it implies that there is something beyond mathematics.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.